Hello everybody, my name is Brandon Renwick, and this is my CSC 180 project number 4. I hope you enjoy it. Okay, so the premise of this project was to solve the 8 queens problem. And that problem consists of having an 8x8 chessboard with 64 total pieces, and the goal of the game is to put 8 queens on the board in such a way that none of them can attack each other in a given turn. This algorithmically would have been hard to do. However, we used a technique called the genetic algorithm, which it uses kind of techniques that we see in nature through natural selection. It mimics those and allows a computer program to kind of drill in on a target goal that you set with what's called a fitness score. So it was very, very cool. It was the first time I've ever seen anything like it, and it was a really fun thing to do. The overall code design is pretty simple to follow once you understand the basics of the genetic algorithm. You start with an initial population, which was either a list of indexes between 0 and 63, or a list of row indexes, which could be cross-referenced with their index in the list to determine their absolute position. You then feed it a fitness function, which gives it a level of fitness depending on what you as the developer want the populations to converge to. So our tactic was to assign fitness scores for every collision and then have it work towards less fitness score to avoid the collisions. You then select a portion of your population and you perform a crossover. I think it's referred to as a mate in the Toolbox API. Where two parents essentially share attributes with their children, and then you have a chance to mutate, and the functions are listed below that were used. And what the mutation does is, just like in nature, most of the time it actually hinders your fitness score, but it also has the ability to randomly present things that are more optimal and more favorable so that future generations can spread them through. And then at the end, when you're done looping through the amount of generations that you like, you then get the best fit generation that you can select from, and hopefully they've solved your problem. So let's talk about the fitness function, since that was definitely the most coding involved in this project. Everything else was pretty laid out or abstracted with the wonderful toolbox through the deep API. So there was really two main inputs, and they are separate, and you'll see why. So there was a position-based list of indices, and then there was a row-based list of indexes that I converted to position only for the purpose of getting a fitness score. The original structure was preserved, and the output or the final generations reflected that, because otherwise I would effectively just be comparing two of the same data. I then wrote an algorithm that you'll see that basically assigns each entry a row number, a column number, and two diagonal numbers, which indicate which row, column, and diagonals that it exists in. I then perform a kind of rudimentary collision detection by just cross-referencing how many total are in each row from each set, and then subtracting that by 1. And then I determine what the fitness score is, and that basically is a summation of all the collisions, plus a pretty heavy bias if the board had duplicate spots. So let's say a queen was put on 0-0 and another one was, that would have resulted in a heavy penalty to encourage the program to select it out. And then the output is finally the fitness score. So the specific kind of code design, showing the code would have been just a nightmare. A lot of it was actually kind of hard-coded. We'll get to that later. So it looked a little ugly. But basically the premise of detecting collisions was having each queen represented by 4 possible kind of positions that it could be in and meet other queens, assuming that it wasn't directly on top of one. And then for every single queen in the set that was along, like, let's say either a row, if there was 3 queens here, there would be 2 possible collisions, since queen 1 could not jump over queen 2. And so that ended up being basically, I drew out all the scenarios, I think it was about all 8 of them in a row. And it turned out that it was consistent with this algorithm right here. So for every queen in a row that's more than 1, you just subtract the total number by 1, and that holds. Furthermore, evaluating fitness was just summing up all of these possible row combinations with the subtraction and then adding a collision penalty if it occurred. So let's see how everything did. So the position index lists were the first one that we tested. And here are the listed hyperparameters. You'll also notice that these hyperparameters did not change. I did adjust the mutation, crossover, generation count, and population size. I found this to be the most optimal. Upping the generation count to 1,000 was actually pretty fun because you got to see a lot more computations being done, but it didn't really affect performance, all things considered. So you see here, it definitely did approach our target goal, especially the minimum. The average sat a little bit on top of the minimum, and you have some peaks and valleys in the average, so there is some variance showing. And then our best individual was able to effectively solve the problem, along with the best individual for pretty much everything after generation 20. So that was kind of cool. Furthermore, the row index actually performed, in my opinion, much better. It converged a little bit slower, but definitely more steady, and the average had no peaks and valleys in comparison to the previous one. So that was, I thought, very interesting. The professor in his lectures was talking about how framing the data is very important in the genetic algorithm, and how you set up your data will directly affect the performance. And so this was kind of a showcase of that concept. And for me, I don't fully understand that, but it's really cool. And so I kind of wondered if there was ways to formulate the data which would even yield more success. A couple of challenges I encountered. Number one, let's talk about it. My Python skills. The parts where you had to get a little bit creative, mainly in detecting collisions, I kind of resulted to a little bit of hard coding to specifically solve the 8 queens problem. I didn't really like doing it, but I was definitely hitting my head against the wall with how to implement some of these things. I wrote out recursive functions that could essentially build up the map and detect collisions, but I just didn't have the skills in Python to really do that. I've sank the last 2 years in primarily JavaScript and doing web application based things. I love the Python language. It's just not something I have broken that huge absolute learning curve on, but I do aim to do so in the future. The second challenge is the deep framework learning curve. This wasn't that big of a deal. Once I learned more about the genetic algorithm, deep made things very easy. You simply add things to the toolbox and you're able to run the algorithm. It's very similar to Keras in that way, where it abstracts out a lot of the things that are punishing that will cause your data to shift too much if you make a mistake. So there was a little bit of a learning curve there, but mainly it was on the concepts of genetic algorithms. So, but above all, this project was a lot of fun, and I've never experienced a genetic algorithm. It's something I would really like to kind of look into in the future because it was extremely interesting. And that concludes my project. Thank you guys. I hope you enjoyed it, and best of luck.